Hi everyone, my name is Vijay Narasimhan and I'm the manager for early stage R&D at EMD Electronics. And I'm so happy that you've joined me today for my webinar on the fundamentals of ferroelectric hafnium oxide based systems to help us make better devices. Here is an outline of what I'm going to be talking about today. So first, I'm going to be giving a motivation to talk about why the semiconductor community is so excited about ferroelectric hafnium oxide and related systems. Then I'm going to talk in the characterizations section about what makes hafnium oxide ferroelectric and how can we go about measuring it. In the third section, I'm going to give a series of examples of how, with an understanding of the mechanisms underlying ferroelectricity in hafnium oxide, we can seek to improve device performance. And finally, I'll conclude with a summary and outlook. So starting with the motivation, what is making people so excited about ferroelectric hafnium oxide? First, let's start by talking about what a ferroelectric is. So here you can see a ferroelectric material that we've sandwiched in between two metal electrodes to make a capacitor structure. When we apply an electric field across this ferroelectric material, we can actually switch it between two different states. One state where the atoms are organized as we can see here, and the other one where the atoms in yellow actually move up towards the top of the crystal lattice. If this were, for example, a metal oxide material, these yellow atoms could be oxygen atoms that move from one position in the lattice to the other. That changes the electron distribution within the material, and therefore this also changes the polarization state within the material. So we've used an electric field to change the polarization state in the material. And furthermore, when we take that electric field away, the polarization state in the material remains, and this is what defines a ferroelectric. Visually, we can see ferroelectricity in the plot of a material's polarization versus voltage, which we have over on the right-hand side over here. And what we have is a loop opening at zero electric field. That loop opening corresponds to 2 times a quantity called the remnant polarization, and again, that's that effective stored charge that we have when we take the voltage away. Historically, ferroelectric materials have been in the perovskite oxide class. So these are things like barium titanate or lead zirconium titanate. There have even been some ferroelectric materials that are organic, like PVDF. About 10 years ago, scientists made a discovery that made the semiconductor community very excited, and they found that hafnium oxide can, under certain circumstances, become ferroelectric. Here, for example, you see a blended hafnium zirconium oxide film that's sandwiched in between 2 titanium nitride electrodes, and when we probe this system electrically, we actually see this open loop hysteresis in the polarization versus electric field response. This discovery is particularly exciting because hafnium oxide is used all the time in semiconductor processing. You can find it, or its sister dielectric zirconium oxide, in gate dielectrics, in transistors, or in the capacitors that work inside DRAM, which make up most of our computer memory. Hafnium oxide is much more compatible with CMOS semiconductor processing than traditional ferroelectrics like lead zirconium titanate. Another reason why this oxide is particularly useful is that it can be deposited by atomic layer deposition, or ALD. ALD is important in the semiconductor industry because it provides precision thickness control and the ability to deposit over very steep step edges. Here we contrast ALD with typical physical vapor deposition, or PVD. So in PVD, you can get really good mixing of materials, but the deposition process, which is usually evaporation or sputtering, is a line of sight technique. So it's really hard to cover surfaces that have large steps in them. In ALD, on the other hand, we use a chemical process. So we start by introducing one molecule into our reaction chamber, and we call this molecule our precursor. It flows and sticks all over the surface, but it doesn't stick to itself. And so basically it saturates the entire surface with one layer of this particular precursor. We then take that precursor out of our reaction chamber and put in a second precursor called a reactant. That reactant goes and then makes a reaction with the surface, ideally producing one atomic layer of the material that we're interested in. We then remove the reactant and we repeat this process. And so we can grow our material in a cycle by cycle, angstrom by angstrom way over very steep step edges by using atomic layer deposition. Bringing this back to hafnium oxide, we can use hafnium precursors like TDMA hafnium or HFDO4 in order to put the hafnium down, and we react it with an oxidant like water or ozone in order to get our film. So having a silicon semiconductor compatible ferroelectric opens the door to lots of new classes of devices that we could use both for memory applications and for logic applications. And I've illustrated two different types of devices on this slide. So on the left, we see a two-terminal device called a ferroelectric tunnel junction. It looks a lot like the metal insulator metal capacitor that we showed before. The key difference here is that we've added an interlayer, or the other alternative would be to change one of these metals so that we have some degree of asymmetry in the energetic landscape in this device. So when the ferroelectric in this system is polarized in one direction, you can have a lot of current flowing through this device. If, on the other hand, you flip the ferroelectric to the other polarization, current is blocked from going through. So by modulating these currents between high and low states, you're effectively creating a way to store data in a non-volatile way. There's even the possibility, depending on your ferroelectric domains, to engineer it so you can access intermediate states in between these two. And so being able to access multiple levels in between an on and an off state would be really useful for something like an artificial synapse for neuromorphic computing. On the other side of the slide, you see a three-terminal device. So this is the typical structure for an MOS transistor, a metal oxide semiconductor transistor. But instead of just having a regular dielectric oxide, we've put a ferroelectric material in the gate of this transistor. So by adding this ferroelectric material and being able to switch it between two polarization states, we could either have a switchable threshold voltage for our transistor, and that allows us, again, to store information in this transistor to make it a memory element. In another particular application, we could modulate the ferroelectric thickness to very closely be tuned to match the capacitance in the dielectric thickness in such a way that we can create an interesting state in the ferroelectric called negative capacitance. Overall, what this means is that the gate going from the top to the bottom has a greater capacitance than you get from either of the components alone, either the ferroelectric or the dielectric. And that, in turn, results in reduced voltage losses, which could result in low-power electronics for logic applications. Down at the bottom of the slide, I've provided some links to references that you can refer to explore more about the different classes of these devices, and also some of the theoretical questions that still remain about using them in semiconductor applications. So now that we've motivated the reason why we want to look at ferroelectricity and hafnium oxide films, it'd be helpful to have an understanding of how we would measure these ferroelectric properties. So in the next few slides, I'm going to present a toolbox of techniques on how we can determine whether a particular film of hafnium oxide is going to be ferroelectric and how well that ferroelectric is going to perform. The key takeaway for this section is that the crystalline structure of a material determines whether it can be ferroelectric. So on this slide, I've illustrated three typical crystal structures that we observe in hafnium oxide and zirconium oxide systems. There's a monoclinic phase, P21C. This is the most stable phase under normal conditions. It's the one that you observe in the bulk, for example, in zirconium ores in nature. We have our orthorhombic phase. This is one where we have oxygen atoms that are slightly displaced in the lattice. It looks very similar to the diagram I showed a little while ago of a ferroelectric. And it's really interesting because this system does not have a center of symmetry, and as a result, it's capable of demonstrating ferroelectric behavior. But unlike the monoclinic phase, the orthorhombic phase is metastable. It doesn't usually exist under normal standard conditions, and so you have to use different energetic tricks, for example, strain, doping, alloying with other materials, and so on, in order to make this phase visible in thin films. There's a third phase that is important as well. It's a tetragonal phase. This one has a very high potential dielectric constant. It's one that's actually pretty commonly observed in zirconium oxide films. So because of the symmetry in this structure, it doesn't have the ability to have an open loop opening, and so it doesn't have the ability to demonstrate ferroelectricity. But you could actually see a pinched ferroelectric hysteresis loop in this case, and so you might observe anti-ferroelectric behavior. It's important to note that although I've talked about these three particular phases, there are many other phases that can exist, and some of these phases that have been demonstrated both in theory and experiment could also demonstrate ferroelectricity or anti-ferroelectricity. So now that we know that what we're looking for, we have to understand how it is that we're going to go about measuring the crystalline structure of a material. And so the standard technique that we use to do that is X-ray diffraction, or XRD. So let's look at this diagram on the left to see what happens when we hit the first couple of layers of atoms in a material with X-rays. We have our X-rays coming in from this side. They have a particular characteristic wavelength. And remember that X-rays are electromagnetic radiation that have wavelengths on the same order as the atomic spacing between atoms in a crystalline lattice. So our waves come in, and they're lined up to start with. And the first wave that we have here hits the top surface of atoms in the material and bounces back out. Our second wave has to travel a little bit further. It goes down to the second layer of atoms, traveling an extra distance, which is equal to 2 times the layer spacing between these layers of atoms times the sine of this angle, theta, which is the incoming angle of the X-ray. So basically, because this wave has gone a little bit of extra distance, it basically has oscillated a few more times. And if the conditions are just right, at the output, what happens is your wave fronts will align, you'll get constructive interference, and therefore you'll see a peak in the diffraction pattern of this system. Mathematically, this corresponds to Bragg's condition, which is illustrated up here, which basically says that as your wave travels in between the crystal lattices of your structure, if it travels a distance that's equal to an integer number of its wavelength, then you're going to be able to see constructive interference, and a peak will form if you take an X-ray diffraction pattern scanning through multiple angles of incidence and reflection. Here on the right-hand side, you actually see what that pattern would look like, and you can kind of think about this like a fingerprint of the crystal structure of the material. So we have the 3 phases that we talked about before for ferroelectric, antiferroelectric, and monoclinic hafnium oxide. And we can see that there are some differences in between the patterns that are produced by these 3 different crystal structures. It is important to note that the tetragonal and orthorhombic phases actually have similar diffraction patterns. And these would be even more similar in the case of a thin film, because nanoscale films have broader, weaker peaks, and so some of these fine features that you have out at higher angles would get smeared out. So the important thing to note, though, is that if you want to achieve ferroelectricity, you definitely can't have the monoclinic phase. And so XRD is really useful for determining that we can suppress the monoclinic phase when we're trying to make a film in favor of these other higher K or higher dielectric constant phases, and that gives you a really good shot of having ferroelectricity. Besides using X-ray diffraction, we can use other techniques to look at the crystal structure of these materials. And here is one of them. It's called extended X-ray absorption fine spectrum. And so this is a probe that allows us to look at the local environment of the different atoms in our crystal lattice. And so here again, we have different views of our different crystal lattices, but this perspective is looking at just a single metal atom and what surrounds it. And if we use this X-ray absorption technique, we can actually get a different set of fingerprints than the X-ray technique that we used before. And so this can make a complementary lens into the crystal structure in our system. The disadvantage of this technique is that it typically requires a high flux of radiation. There are some laboratory instruments available, but most of the time you would do this kind of measurement at a synchrotron. And even when you're doing it at a synchrotron, it's a pretty long measurement. In order to get meaningful signals out of it, you sometimes have to measure one sample for a series of hours. And so it isn't something that you might use all the time, but when you're trying to gain mechanism understanding, this or other techniques that probe local structure can be really useful lenses for looking at what's happening in a material. And finally, the standard technique for finding out whether a material is ferroelectric is to measure its polarization voltage plot, to measure it electrically. So the typical way that we do this is that we make a capacitor structure where we have a pattern top electrode, a blanket bottom electrode, and then our ferroelectric layer in between. And then we probe it electrically using a triangular waveform. And by sweeping this triangular waveform of voltage over time, we are able to derive the capacitance versus voltage plot, and in turn, the polarization versus voltage plot that tells us whether we have an open loop opening or not. Sometimes we also apply a square wave to the system. This is basically a wake-up procedure. It is a procedure to get better electrical performance out of the system. For example, if you have a pinched ferroelectric loop to start with, sometimes running an electrical stress or wake-up procedure will open that loop up, and you'll get a nice ferroelectric curve as a result. And you can cycle in between these two techniques in order to see how far you can push the electrical performance of your system. But overall, by inputting this triangular waveform, we're able to see whether we have a straight line here, a pinched loop, or an open loop, and that might tell us a little bit more to correlate with the physical measurements that we took of the crystal structure that we saw before. So now we have this toolbox of techniques that we can look at to see whether a material is ferroelectric, both from a physical perspective and an electrical perspective. And so in the next few slides, I'm going to take a look at some ways that we can actually influence the structure of a material in order to boost the performance of devices. It turns out that the crystal structure and the ferroelectric behavior of hafnium oxide can be influenced by a huge variety of processing conditions, literally at every step, even in making this simple metal insulator metal structure in the capacitor form. For example, you can start with the bottom electrode. What material are you going to choose with the bottom electrode? Does it have a particular crystallographic orientation? Will the bottom electrode migrate into your ferroelectric layer, or does it extract any oxygen from your ferroelectric layer? The ferroelectric layer itself, you can make it through different processes and using different materials deposited at certain temperatures. You can change the times at which you're dosing the precursor and the reactant. You can introduce dopants, you can introduce alloys, or you can make nanolaminates. And then you can repeat everything that you did on the bottom electrode on the top electrode as well. It's important to note that in most ferroelectric hafnium oxide systems, you tend to deposit your material amorphously, so it doesn't have any crystal structure to begin with. And so in order to be able to exhibit ferroelectricity, we do need that non-centrosymmetric crystal structure, and so we might need to apply a thermal profile onto this sample in a particular ambient at a particular ramp rate and up to a sufficiently high temperature in order to get crystallization. And then also, of course, the electrical profile can affect things, as we saw before. If you input just a triangular wave, you might see one ferroelectric response, but then by stressing the system electrically, you might see more. And so let's walk through a subset of examples from this wide parameter space to illustrate ways in which you can do studies to dive deeply to understand process structure property relationships in order to give pragmatic solutions for improving the ferroelectric performance of capacitor stacks. So first, I'd like to talk about some experiments we did about combining hafnium and zirconium oxide together. So shortly after the discovery of ferroelectricity in hafnium oxide and doped hafnium oxide systems, people started looking at mixing hafnium and zirconium oxide together. The reason that this is such a natural fit is because hafnium oxide and zirconium oxide are literally like two peas in a pod. The way that hafnium was discovered as an element was that people knew that there was a missing element at position 72 in the periodic table, but they didn't quite know where to find it. They had an inclination that it was going to be chemically similar to zirconium oxide. And so they started looking and eventually found hafnium oxide very closely intermixed with zirconium oxide in zirconium ore samples, so rocks that you get out of the earth. And so the reason that these two materials go well together is because they have very similar crystal structures. And so whether you're talking about hafnium oxide or zirconium oxide, you actually can position the atoms in very similar orientations to what we talked about previously. And by scanning in between a range where you have almost entirely hafnium oxide to almost entirely zirconium oxide, you can really illustrate all of these different crystal structures and all of these different electrical responses, going from a regular dielectric material to one that has an open loop ferroelectric response to one that's more of a pinched loop antiferroelectric response. And so this is a really powerful way that you can tune your system in order to get different electrical properties. But as it turns out, you don't actually need to mix the zirconium oxide and the hafnium oxide so closely together in order to get ferroelectricity. In this case, what we're showing is that by depositing a bilayer film, where you actually have distinct nanometric layers of zirconium oxide and hafnium oxide into capacitor stacks, you're actually able to get an open loop hysteresis in the polarization voltage plot. You're able to get a ferroelectric material. But what's really interesting about this is that the order really matters, is that whether you put zirconium oxide on the bottom and hafnium on the top, or vice versa, has an effect on whether, or has an effect on the size of the remnant polarization in your sample. These loops are open to different extents. And so, in a study we did a couple of years ago, we really wanted to look at whether this electric behavior correlates with the atomic structure in these different layers. And so, we wanted to use some of our physical lenses to look at that problem. We started by using the XAFS technique that I talked about before to look at the local environments of both hafnium and zirconium atoms in these two different types of structures, the nanolaminates with zirconium on top versus hafnium on top. Here you can see the signals that we get out of the XAFS process and the fingerprints that we can apply by combining different samples that we know the crystal orientation of in linear combinations in order to get a pattern that closely matches the spectrum that we get out of the X-ray absorption experiment. By doing this, we're able to back calculate what fraction of each of the three phases we have in hafnium oxide and zirconium oxide. If we just use this XAFS technique, there's actually a lot of uncertainty in this measurement because the orthorhombic and tetragonal structures are very different in XAFS, but the orthorhombic and monoclinic structures are very similar. And so as you can see, particularly for hafnium oxide, there is a wide degree of variability that you get in the estimates for how much of each crystalline fraction that you have in this film. My colleague Martin McBriarty developed a clever technique to complement this XAFS analysis with X-ray diffraction. So remember, in X-ray diffraction, it's hard to tell the tetragonal and the orthorhombic phases apart. In XAFS, it's hard to tell the orthorhombic and monoclinic phases apart. But when you put these techniques together, you can actually start to clamp down and hone in on what these different crystalline fractions are. In doing this, Martin made a really interesting discovery, which was that most of the difference in the ferroelectric performance of this device doesn't come from the hafnium oxide layer. It comes from the zirconium oxide layer. As you can see here, depending on whether zirconium is on the bottom or the top, the percentage of ferroelectric orthorhombic fraction changes dramatically between those two conditions. So zirconium oxide crystallizes at lower temperature than hafnium oxide, and therefore it has a higher density of randomly oriented crystallites. And this type of crystallization favors the orthorhombic ferroelectric phase. So through this set of experiments and really understanding what's happening in each layer of the stack, we're able to see that annealing these samples with zirconium oxide on the top, basically as a free surface, yields a higher orthorhombic phase fraction and therefore a higher ferroelectric loop opening than when it's the other way around. And so you can see how this mechanistic insight really does influence the pragmatic, practical ways that we would build a device in order to boost the ferroelectric performance. We can also take this a step further, is we can really start to reduce the thicknesses of these different layers. So, we can start with, say, a bilayer film of hafnium oxide and zirconium oxide with zirconium oxide on the top. We can reduce the thickness of those layers by half and then increase the number of layers, or we could do that again. So you have 2 layers, 4 layers, or 8 layers total. And in a study done by my colleague Stephen Weeks, he found that using this approach, the system that actually has alternating 1 nanometer layers of hafnium and zirconium oxide with the zirconium oxide on top of the hafnium oxide as deposited actually has a larger remnant polarization than what you get out of the fully blended film, out of making intimately blended mixes of hafnium and zirconium oxide together. And so, again, using that mechanistic insight to understand which order to put the films down in and then going further with experiment to figure out how to tune those conditions, we were able to make ultra-thin multi-layers that showed better ferroelectric performance than solid solutions. So building on the fact that we can see how important interfaces are on affecting the crystal properties in the systems, next, I want to take a look at a couple of ways that we can influence the ferroelectricity of hafnium oxide outside of the ferroelectric material itself. So for this particular experiment, we're looking at a material that leans a little bit more towards the zirconium oxide end of that hafnium-zirconium oxide blend. We have a fully blended film, but again, it starts to lean more towards zirconium. And as we discussed before, typically what this results in is a pinched loop opening. And so here what you can see is that when you run your ferroelectric hysteresis curve, you get a pinched loop opening, and even after field cycling, you do still see some amount of pinching. This is the standard structure that we would use, is using an ALD titanium nitride electrode at the bottom and a PVD titanium nitride electrode on top. And that gives just the response we'd expect, right? So this anti-ferroelectric type response. If we were to replace that bottom titanium nitride electrode with an iridium electrode, a different metal, we actually see that after stressing the system, we get a nice wide loop opening. This is actually a very significant remnant polarization that we see in this system. To understand why that is, we wanted to see what was happening with the crystalline structure of the ferroelectric and relate that to the crystalline structure of the underlying electrode. It turns out that when you deposit iridium by ALD, it tends to be highly textured. That means that it has crystals that are oriented in specific directions. It turns out that that orientation actually seems to orient the ferroelectric film as well to a certain extent. So if we look at the way that that orthorhombic peak is oriented with respect to the substrate using a pole figure plot in XRD, we actually see a much tighter distribution of that particular crystal peak, which means that the crystals are much more closely aligned in the iridium system than they are in the titanium nitride system. So the overall takeaway from this slide is that the bottom electrode choice can really enable the ferroelectric response in a more zirconium-rich solid solution after wake-up. So not only does it modulate the response, but this could have very favorable effects because zirconium oxide tends to have better leakage performance than hafnium oxide does under certain circumstances, or there might be an integration reason that you might want to pursue one type of electrode over another. And understanding these differences can really help to explain the effect of those integration differences or those composition differences on what you're seeing in the electrical response of your device. This next study is really interesting because it shows how you don't necessarily have to do an experiment in order to see the effect that a particular parameter can have on ferroelectricity. So my colleague Sergey Barabash here has done a simulation study to find out what happens when a ferroelectric material changes from one polarization state to another, when it flips from one to the other. And this can be modeled by showing the ferroelectric being in two distinct atomic states, but then going through a transition state in the middle. This is the one that was most commonly previously reported, but through this analysis, Sergey discovered that there are alternate pathways that could also be possible in this system. A really important part of this study was that Sergey identified that strain can strongly affect which of these pathways gets chosen. So strain you can impart into a ferroelectric capacitor, for example, by changing the electrodes to have different coefficients of thermal expansion. You also might apply a different thermal profile to the system, or maybe you could even add dopants or alloy the ferroelectric material itself. And all of these things will affect the stresses on the material and then in turn the strain. And by modulating the strain, you can actually change the mechanism by which the device switches between its polarization states. This could be really important because ultimately this will have an effect on the coercive field, for example, in the sample, and that is a key parameter on the electrical polarization versus voltage plot that tells you how much voltage you need in order to switch this system from one state to another. And so again, not just our experimental lenses that we used before, but simulation lenses can really help us understand the mechanism underlying things and then go after experimental pathways that support those mechanisms in order to get us the electrical performance that we want. So one fact I haven't talked a lot about so far is temperature. So as I mentioned a little bit before, many hafnium oxide systems, when you deposit them, they're amorphous. They don't have any long-range crystalline order, and therefore they can't be ferroelectric as deposited. Therefore, thermal treatments can have a profound effect on the crystal structure of these hafnium oxide-based films. As an example, let's compare two ALD hafnium oxide films that are annealed in a rapid thermal annealer. An RTA, or rapid thermal processor, or rapid thermal annealer, this is basically the easy bake oven of the semiconductor industry. You have your sample in here, it's heated by these very, very powerful lamps, and it can be heated very quickly from room temperature up to 700 or more degrees Celsius in a matter of seconds. What we observe is when we heat the film rapidly at 50 degrees Celsius per second ramp rate, we actually get a really nice strong orthorhombic ferroelectric peak in the system. However, when we heat the film at a much slower rate, say 10 degrees Celsius per second, the orthorhombic peak is much more muted. So the important point here is that in a rapid thermal annealer, the changes that we are observing in the crystalline structure of the material are influenced by temperature transitions that are happening on the scale of seconds. And so in order to be able to figure out what's going on here at a more mechanistic level, we need a technique that's able to tell us the crystal structure of this material on the same scale as that thermal transition is happening. To do this, we turn to our collaborators at the SLAC National Laboratory in Stanford, California. And so what we're trying to do in this particular setup is run our annealing experiment in an environment where we could measure the X-ray diffraction signal really quickly. So SLAC operates a synchrotron. This is a type of accelerator that is able to give off very powerful X-rays that have very high flux. So you have a ton of X-rays that are able to shoot at your sample. If you combine that very high flux of X-rays with an area detector that's able to measure your entire X-ray diffraction plot all at once, instead of taking one measurement and getting one X-ray diffraction pattern every 20 minutes or so, you're able to do this on the second scale. Every single second, you can get one frame that tells you all of the crystalline information about your sample. So by sticking this rapid thermal processing chamber into this path, we can actually in situ probe what's happening when we heat the sample up at different ramp rates in order to observe the changes to the crystal structure that happen. So what we found through the study is actually pretty incredible. It turns out that all of the films that we were annealing initially crystallized into the ferroelectric phase, as shown by the arrows in these two diagrams. However, as time runs on, which is what's going on in the y-axis here, if we heat the film slowly, we actually see this orthorhombic peak disappear and the monoclinic peaks appear. On the other hand, if we ramp quickly, while the monoclinic peaks do still emerge, you preserve a large part of this orthorhombic signal in the final film. So when we heat the film more quickly, more of the orthorhombic phase remains, and therefore we would expect this film to be more ferroelectric. This type of measurement doesn't just paint a pretty picture of what's going on in the system, it actually helps us to mathematically model what's going on in the system in order to make pragmatic solutions for how to make our film more ferroelectric in the end. So by looking at the transformed phase fraction, how much of the film switches from this orthorhombic phase to this monoclinic phase over time, we can make a diagram like what I've illustrated here called an Arrhenius plot. From this diagram, we're able to extract a straight line, and then we're able to model an energy barrier. What is the barrier that's preventing this sample from transitioning from the orthorhombic phase to the monoclinic phase? And in doing this type of analysis, we actually found that that barrier is really high. It's over 1 electron volt. And so what that means is that we actually have a shot of trapping this material in the ferroelectric state by minimizing the time that it spends over its crystallization temperature. Basically, because it's so hard for the system to climb over that energetic hill, if we give it fewer opportunities to climb over it, we might be able to get the structure stuck in a metastable state, the ferroelectric state that we ultimately want. This diagram shows that this is in fact the case. So when we test the ferroelectric performance of a sample that we annealed at a slow ramp rate versus one that we annealed at a fast ramp rate, we're actually able to increase the remnant polarization by more than a factor of 2 by annealing it at a much quicker ramp rate. And so by using the learning from this annealing study, we're actually able to have a dramatically improved device performance in a capacitor stack. So in the last set of examples that I just talked about, we showed that how we can drive a ton of transformation of the crystalline phases of a material depending on how we anneal it. Do we anneal it quickly or slowly, and to what temperature? But wouldn't it be nice if we didn't have to deal with the vagaries of annealing and could just get a material that's deposited in the right structure from the get-go? The core question we were trying to answer in this next study is whether we could have a crystalline film as deposited that demonstrated ferroelectricity. So to do this, we needed to start with different precursors than the one that we normally use for our ALD processes. Standard amide precursors have ALD windows, or suitable deposition temperatures, that are at or below the crystallization temperature of the oxides, hafnium oxide and zirconium oxide, that we're interested in. On the other hand, these advanced metallocene precursors, HFDO4 and ZrDO4, can really push that ALD window much higher. And therefore, now you're in a temperature space where you actually could see some crystallinity in the material as you deposit it. And so the question, knowing this behavior about these precursors, is would that type of film be ferroelectric if we engineered it properly? When we started looking at this material, we discovered a sweet spot in the deposition temperature and reactant range. So what we see here is that when we use ozone as a reactant and we use a deposition temperature of 300 degrees Celsius for zirconium oxide, at any thickness from around 5 nanometers almost all the way up to 20 nanometers, we never see a monoclinic peak emerge in the as deposited film. This is really unusual. If you look at the 340 degree case of the same situation where we're using ZrDO4 with ozone as the reactant, you can see that, in fact, the thicker that you go, you get a very strong monoclinic peak emerging. It could be as much as half of your sample is in the monoclinic phase. So we were pretty confident that we actually have a robust non-monoclinic phase in zirconium oxide when we can lower the deposition temperature to 300, right on the range where it starts to crystallize, but below the range where you start to have the monoclinic peak come into play. And so starting with this, could we combine this with HFDO4, the sister precursor, at the same deposition conditions in order to develop a mixed hafnium and zirconium oxide film that demonstrates ferroelectricity? So the combined zirconium and hafnium oxide film does show less than 20% monoclinic phase signal, and it's still really crystalline as deposited. As a result, we were able to demonstrate a nice ferroelectric loop opening without any subsequent processing in this film. No fancy anneals at all. And this was really exciting because it gives us more flexibility in the choices of electrodes and thermal annealing conditions that we could use. And that really could allow us to make our process for making ferroelectric capacitors more compatible with a variety of semiconductor fabrication workflows. That last remark about making ferroelectric capacitors more compatible with semiconductor processing in general is a good segue into our summary and outlook. We've seen that ferroelectric hafnium oxide is a really exciting and promising material for computing technologies, and that there's many process knobs that we can tune in order to optimize the ferroelectric performance. Beyond just doing experiments, we saw how mechanism understanding can really provide a pragmatic recommendation and additional lenses into how we would ultimately make our device stacks. To really develop a semiconductor ecosystem that supports ferroelectricity, though, we need to still overcome some challenges. These include scaling, integration, retention, endurance, and multi-level switching for neuromorphic computing. What I really hope is that seeing all of the examples we talked about in this presentation and the tools and toolbox that I presented, that we will inspire you to work on tackling these challenges and to do so with a material-first perspective. Thank you again so much for joining this webinar today. I'm really thankful that you took the time out of your day to learn more about the materials aspects of hafnium oxide ferroelectrics. If you want to connect with me to ask me more questions about any of the studies that I've done or ways that we could collaborate in the future, please go ahead and reach out to me. You see my email address on the screen, or you can also contact me by LinkedIn. I'd also like to give a big thank you to all of my colleagues and collaborators over the years who have done such excellent work in this field and contributed a lot of the material to this presentation. And I also want to thank you again and hope to work with all of you in the future. Thank you and have a great day. Bye-bye.